The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I will respond as soon as I can. All right, so today we're going to start chapter 8 and we're going to begin with section 8.2. We'll spend today on it and then we'll spend Monday on the second part of 8.2. So let's go ahead and get started. All right, let's say we have a bunch of people and their names. So let's say we've got John, Jose, Alice, and Maria. Okay. And over here, we're going to have their birth dates. John was born on June 1st. Jose was born on August 10th. Alice was also born on August 10th, and Maria was born on May 8th. Now, this represents a bit of reality, and that is this. Each person has one birthday, discounting religious experiences, of course, but each person has exactly one birthday. You could have two people with the same birthday, such as Jose and Alice, but you would never have one person with more than one birthday. For instance, Maria's birthday is May 8th. It couldn't also be, let's say, March 3rd or whatever, okay? In other words, each person has exactly one birthday, but more than one person can have the same birthday. The way this relationship works is the same way that a mathematical relationship works, that is called a function. I want to point out that function starts with fun. How great is that? But it ends with shun, and we know what it means to shun someone. But anyway, back to the story. All right, I want to read to you what it says in the textbook about a function. It says a function is a set of ordered pairs, a relation, in which to each first component there corresponds exactly one second component. In other words, everybody's got just one birthday. The set of the first components is called the domain of the function, and the set of second components is called the range of the function. So, domain, range. So let's say we've got 1, 2, 3, and 4, and over here 5, 7, and 12. And let's say that 1 goes to 5, and 2 goes to 7, and 4 goes to 7, and 3 goes to 12. This is a mapping that represents a relationship called a function. For each one of the first components, there is exactly one of the second components. Again, you can still have two first components going to the same second component, but you can't have one first component going to more than one second component. If you do that, it's not a function. That can happen, but it's not called a function. All right, so let's look at some relationships to determine whether they are or are not functions. Okay. Actually, before we do that, let's look at some other names for domain and range. You could say input, output, first coordinate, second coordinate in an ordered pair, x value, y value. Let's see here, independent variable, dependent variable. Let's see here. Is independent spelled A-N-T? I can't remember. Independent is E-N-T, so it's probably E-N-T as well. All right, anyway. Cause, effect. So these are all different ways of describing domain and range, okay? Now, let's take a look at the following situation. We have a set of ordered pairs, 7 comma -1, -1 comma -1, -5 comma 3, and 8 comma -6. Does this represent a function? Well, let's see. Each input goes to just one output, right? Now, 7 and -1 as inputs both go to -1 as an output. That's okay. 2 inputs can go to the same output. Let's see. The domain would be what? -5, -1, 7, and 8. Notice I put them in increasing order. So all the X values. The range would be, let's see, -6, -1, and 3. I don't need to list both -1s for the range. I just need to list all the unique values. So there's your domain and range. Any questions about that example? Okay.
No.
Let's take a look at another relation where we have, let's see here. This is 10, 20, and 30. This is 20, 40, and 60. And they have this relationship. Again, whenever you have a mapping like this, the domain is first, the range is second. So yes, this is a function. Each input goes to exactly one output. Okay, let's take a look at another example. Let's see, -4, -2, 0, 6, 8, 10, and 12. -4 goes to 6, -2 goes to 8, 0 goes to 10, and 0 goes to 12. Not a function because you've got what? 0 going to 10 and 0 going to 12. So there is an example of 2 ordered pairs where the same input goes to 2 different outputs. Any questions about that? Okay.
How do you got that one? That you said that is not a function?
Yes. Why is that, you say?
Yes.
Because you have one input going to 2 different outputs.
Oh, okay, okay.
That's
okay.
like one person having 2 birthdays. So 0
Okay.
goes to 10, 0 also goes to 12. Now, this could happen, but it's not a function. So
Mhm.
we're describing specific situations where it's a function. All right. How about this one? Function or not? Yes, it is. You've got 3 inputs with the same output. Triplets, 3 people with the same birthday. So yes, this is a function. Whoops, just a function. All right. What about this one? Let's see here. -7 or -2, 7, -1, 10, 0, 13, 1, 16. Is this a function? Yes. Each input goes to just exactly one output. So yes, it is a function. What about this one? You never make those things. This is not a function. Why not? Because -3 goes to 8 and -3 goes to 12. So these two ordered pairs contradict the way a function works. So you've got one input going to more than one output, not a function. You okay with that?
Yes.
All right. Let's look at it in a table form. How about this one? Is this a function or not? Yes, you've got 4 inputs going to the same output. That's okay. You can have a whole bunch of inputs going to one output. What about this one? No, you've got one input going to more than one output, so it's not a function. All right. You think you got that idea okay?
Yes.
All right. Let's look at the second idea for today, and that has to do with, oops. Function notation. Okay. Now, let's take a look at an ordinary linear equation. Y equals 2x plus 3. And let's say we want to complete a table. And we'll pick some x values. How about -2, -1, 0, 1, and 2. So if x is -2, y would be 2 times -2 plus 3, which is -4 plus 3, which is -1. You okay with that?
Yes.
Okay. If x was -1, y would equal 2 times -1 plus 3, which is -2 plus 3, which is +1.
Mhm.
If x is 0, 2 times 0 plus 3 is 0 plus 3, which is 3. If x is 1, 2 times 1 plus 3 is 2 plus 3, which is 5. And if x is 2, 2 times 2 plus 3 is 4 plus 3, which is 7. So for this linear equation, here are 5 ordered pairs that represent points on a graph. The x values would be the domain, the y values would be the range. Notice for each domain value, there is only one range value. So this describes a function. Now, we can use function notation, special notation, to tell the reader that this y equals 2x plus 3 does behave like a function. And what we're going to do is we're going to take y and we're going to replace it with something called f of x. Now, let's analyze this thing. We have the letter f, and it's written in italics. It doesn't have to be, but it is. And then we have parentheses x. We've learned that something in parentheses is often multiplied. So this looks like it's f times x, but it isn't, okay? Also, we learned back in, if you're looking at percent problems, what is 7% of 10? The word of can mean multiplication in certain situations. And a minute ago, I called this f of x. So it looks like multiplication, f times x. It sounds like multiplication, f of x, but it's not. It's a single symbol. This whole thing is the function notation for y, for the output, okay? Now, the way you use this notation, if we were to write y equals 2x plus 3, but using function notation, it would look like this. F of x equals 2x plus 3. If we wanted to find the same values that we found here, this is how we would go about it. we would replace the X that's in the parentheses with the input value. So to find this ordered pair, we would say f of -2 equals what? How would we find the what? The same way we did over here. We'd put -2 here, and then we'd put it in here. So we get 2 times -2 plus 3, which is -1. So f of -2 equals -1. That is the function notation equivalent of the table notation, equivalent of the ordered pair notation. So these are 3 different ways of saying the same thing, representing that when the input is -2, the output is -1. Here it's an ordered pair, here it's an ordered pair in a table, and here it's being using function notation. So we're not really doing anything new here. It's just the way that we're writing it. We're completing ordered pairs. So to find this ordered pair using function notation, you'd say f of -1. And then the next one would be f of 0, f of 1, f of 2. So f of -1 would be 2 times -1 plus 3, which is 1. F of 0 is 3, f of 1 is 5, and f of 2 is 7. And yes, I just looked over here because the results are going to be the same. Any questions about this whole idea of function notation? All right. Now, when we're using variables, we typically use X and Y. We can use other letters, but those are the ones most popular. Likewise, when using function notation, the most popular one is to use f of X in place of Y. But it's not limited to that. We can have basically any 2 letters. For instance, let's say this was a business algebra class, and we were talking about a profit function. It would be P of X equals something. A revenue function would be R of X equals something. A cost function might be C of X equals something. P for profit, R for revenue, and C for cost. Okay. In each case, X would be whatever the input is. So again, it's not limited to just f of X. All right, let's take a look at some examples. Let's say we have the following. F of X equals -4x. And I want to find f of 3 and f of -1. So to find f of 3, I'm going to put 3 in the place of X on the right side of the equation. So f of 3 is -12. Any questions about what I did there? All right. F of -1 is -4 times -1, which is 4. So f of -1 equals 4. Again, any questions on that example?
No, thank you.
All righty, let's take another problem. Let's say f of X equals 3x minus 5. And again, we want to find f of 3 and f of -1. So f of 3 is 3 times 3 minus 5, which is 9 minus 5, which is 4. So f of 3 equals 4. F of -1 is 3 times -1 minus 5, which is -3 minus 5, which is -8. So f of -1 equals -8. So again, we're using the same idea that you'd use completing ordered pairs in regular notation, putting the input value in place of the X on the right side. Okay. Notice that the input goes inside and the output is on the outside. Input, output, domain, range.
Mhm.
All right, let's take a look at another example. Let's see. G of X equals 5x squared plus 2x plus 2. Let's find g of 2 and g of 3. So again, notice we're using g of x instead of f of x now. So 2 goes in the place of x on the right side of the equation. So we get 5 times 2 squared plus 2 times 2 plus 2. 2 squared is 4 times 5 is 20, plus 2 times 2 is 4, plus 2 is 26. So g of 2 equals 26. If we were to graph this function, one of the points on the graph would be 2, 26. And we'll be doing that later when we get to chapter 10 or 11. I can't remember, but we'll get there. All right. G of 3 is 5 times 3 squared plus 2 times 3 plus 2. 3 squared is 9 times 5 is 45 plus 2 times 3 is 6 plus 2. 45 and 6 is 51, 52, 53. So G of 3 is 53. Okay with that?
Yes.
All right. Good to go on?
Yes.
Let's say we have h of x equals the absolute value of x minus 5. We are to find h of 5 and h of negative 2. Recall when you take the absolute value of a number, it's positive unless it's the absolute value of 0, in which case it's 0. So h of 5 would be the absolute value of 5 minus 5. But the absolute value of 5 is 5, and then you've got a minus 5 outside, so you get 0. So h of 5 equals 0 for this given function. H of negative 2 is the absolute value of negative 2 minus 5. But the absolute value of negative 2 is positive 2, and then minus 5 would be negative 3. So h of negative 2 is negative 3. Any questions about that example?
No, I'm just writing it down.
Okay.
Okay, I'm done.
All right. Here's another example. H of x equals x squared plus x minus 2 all over x squared minus 5x. Let's find h of negative 2 and then h of 5. Okay, so h of negative 2, we're going to put negative 2 in the place of x, every place it appears. So negative 2, the quantity squared, plus negative 2 minus 2 over negative 2, the quantity squared, minus 5 times negative 2. So there's our initial replacing. Negative 2, the quantity squared, is negative 2 times negative 2, which is positive 4. And then we've got plus a negative 2 minus 2. 4 plus negative 2 is 2. 2 minus 2 is 0. So the numerator of this fraction is 0. In the denominator, negative 2, the quantity squared is 4. And then minus 5 times minus 2 would be plus 10. So we get 0 over 14. But 0 divided by a non-zero number simplifies down into just 0. So h of negative 2 equals 0. Let me know when you're done with that. We'll go on to the next example.
I'm done.
All righty. H of 5. We get 5 squared plus 5 minus 2 over 5 squared minus 5 times 5. 5 squared is 25, plus 5 minus 2 is 30, minus 2 is 28. 5 squared is 25, minus 5 times 5 is 25. 25 minus 25 is 0. So we have 28 divided by 0. Do you remember what the answer is when you're dividing by 0?
Undefined.
Correct. Undefined. Good job. People don't often remember that. Now, because h of 5 is undefined, that means that 5 is not an acceptable input to this function. So if you put a number, an input, a domain or x value into the function, do the calculations, and out comes undefined, that means that that input is not in the domain of the function. Okay, so we would say x cannot equal 5. Domain, and we'll talk more about that later, but okay. In fact, well, let's talk a little bit more about that now. When I was a child, I can remember that my mother had a meat grinder, and it was this machine that you put like roast beef, cooked roast beef or something into the machine, and you turn the crank and it came out. It actually kind of looked like worms coming out the side, but it tasted great, even though it looked kind of weird. But one day my brother took a rock and stuck it in the meat grinder and turned the crank. What do you think happened?
It broke.
It broke, right? A rock is not something you put into a meat grinder. It wasn't called a rock grinder. It was called a meat grinder, right? So
Yes.
a rock would not be an acceptable input. And by the way, that story isn't true. So if you know my brother, don't tell him I'm telling naughty stories about him. He didn't really do it, but you get the idea, right? Okay. So 5 is like putting a rock in a meat grinder. It doesn't give us an acceptable output. Okay. Let's see here. I know what I need to do next. So I just turn the page. So let's say we have g of x equals 2x. All right. So what's g of 4? How would you get the answer? I don't want the answer. The answer is 8. We'll get there. But what would you do to get g of 4? What would you do?
Put it where all well, we don't have it. That's weird. That normally we would put it if we had a G, but it's an X.
No. We put what's inside. This is replacing x.
Yeah, so that would be replacing it.
Yes, there you go. So 2 times 4, which would be 8, right?
Yeah.
Okay. What if we had g of -7? What would we do?
Replace it as well.
We'd replace x with that as well. What if we had g of star? I can't make a very good star, apparently. There. What would g of star be?
Well, we will need to replace as well, but
Yeah. Don't go, but don't overthink it. We need to replace the x, right? So we get
yes,
star, right?
whatever we get, we replace it.
Bingo. Exactly. What about g of Sam?
Same thing.
So it'd be 2 times.
Sam.
Oops, I keep wanting to write same instead of Sam. All right. Yeah. Okay, now, with that in mind, let's do the actual problem. It says find g of w and g of w plus 1. Now, don't overthink it. Don't change it. Just do what you did before. So what's g of w going to be?
We're just gonna replace the W, the X with the W.
So we get
GW G times W.
That's what we had. No, not G times W.
No, well, we get G, we're replacing, oh yeah, that 2 times W.
There you go, 2 times W, right? Okay, what about G of W plus 1? What would we get?
We would get 2 times W plus 1.
Excellent. And then this, we could go on and write 2W plus 2. So again, what, in fact, in general, we could say this. G of equals 2 times, and whatever goes in the 2 times.
Yeah.
Okay. All right, let's do another one. Let's say we've got G of X equals 2X minus 7. And we're going to find G of W and then G of W plus 1. So what would G of W be?
2 times W minus 7.
Excellent. Okay, here we go again. G of W plus 1.
We would change it to 2 times W plus 1.
Like that?
No, in parentheses,
Good job.
minus 7.
Excellent. And then you'd get what? 2W plus 2 minus 7, which is 2W minus 5. By Joe, I think you've got it. All right, now, what we've been doing, we've been putting in X values or domain values and doing the calculations and getting the output or the range values, putting in the X and finding the Y, putting the input in, finding the output. Now we're going to switch things up a little bit, okay? Let f of X equal negative 2X plus 5, okay? For what value of X does function f have the given value? And it says f of X equals 5. All right, what we're doing is this. Let's come back to this in just a minute. Let's say I have this, y equals negative 2x plus 5. And I have this table, okay? And maybe it's got 0, 1, 2, etc. What if it had this? What if I had this with this equation? How would I determine what x was?
Putting the 5 and the Y.
Exactly. Now, again, don't overthink this. The reason I keep saying that is because people take this thing and they make a whole lot more out of it than they should. I've got this function, f of X equals negative 2X plus 5. For what value of X does function f have the given value? So in other words, what's the input when the output is 5? So this is going to go in the place of all of that. We're not going to find f of 5. That would be x is 5. We're going to write 5 equals negative 2x plus 5. So we put the output value in the place of the whole symbol f of x. And now we solve to find the input. Subtract 5, 0 equals negative 2x. Divide by negative 2, x equals 0. So you'd say, for what value of x does function f have the given value? X equals 0. So 0 is the input that produces the output. Okay.
Okay.
Let's go back, way back to, let's see here, to here. What if I said, who has a birthday on June 1st? What would you say?
John.
Who has a birthday on May 8th?
Maria.
Who has a birthday on August 11th?
Jose and Alice.
Right. So it's the same kind of thing. I'm giving you the output, asking you what input leads to that output. Okay.
Okay.
All right, now let's go back down here. And let's see here. Let f of x equal 3/2 x minus 2 for what value of x does function f have the given value? And we're going to say f of x equals -1/2. So who is it that has a birthday that's -1/2, so to speak? So what are we going to do with the -1/2? Where's it going to go in our function?
We're gonna replace it with the x, the 3, it would be 3, 2 times 1/2.
No,
Minus.
no. This is not x.
Oh, yes,
That's the output. So where's that going to
Yeah.
go?
at the output outside.
So right there.
Yes,
It's going to replace the whole thing. Okay?
yes.
All right. So we're going to get that situation.
Yes.
Okay. So now let's see. Let's add 2 to both sides. So we've got -1/2 plus 2 equals 3/2 x. Or you know what? Let's go back. Let's clear the fractions. Let's clear the fractions out. We'll do that first. So we'll multiply both sides by 2. So we get -1 equals 3x minus 4. Are you okay with what I just did there?
You multiply the denominator, right?
Yeah, I took 2 times -1/2, which is -1.
Yes.
2 times 3/2 x, the 2's would reduce down, giving us 3x. And then 2 times -2 is -4 or -4.
Oh, yeah. Got it.
Okay, then we'll
Yes.
add 4 to both sides. So we get 3 equals 3x. We'll divide both sides by 3 and x equals 1. So for what value of x does the function f have the given value x equals 1? So in other words, f of 1 equals -1/2. But they gave us the output and asked us what input produced it. So this goes in place of the entire y value or f of x value. It's not the insight, it's not the input, it's the output, the whole thing. All righty?
Yes.
Okay, well, that's all I've got for you today. On Monday, we'll continue with section 8.2, part 2. I'll be back this afternoon with an office hour at 1:15. Excuse me, should you have any questions? I'm going to go ahead and stop the recording.